Thank you so much. Appreciate it. All right, let's get this going. Everybody see the screen? Perfect. All right, well, I'm presenting a study that was done today, and essentially this study was centered around making the case for ERVs in multifamily high-rise buildings. So there we go. All right, so this was for a specific project in New York City Metro. And we wanted to make the case for ERVs within the apartment spaces. So the project already had energy recovery ventilators in the common spaces. We wanted to try and get them in the apartment spaces as well. So this was, at the time of design, was a 16-floor multifamily high-rise, about 134,000 square feet, some common area and community facilities. And the case we wanted to make, we wanted to look at air quality and energy consumption of various ventilation strategies. We wanted to look at infiltration only as sort of a baseline, and then compare exhaust only strategies versus energy recovery ventilators and show the impact of envelope air tightness on these factors. And initially, we had the idea to look at respiration and see if we could see how CO2 levels changing due to respiration, if that could be a motivator to sort of encourage better air quality. We later added filtration to the study as well. So in order to minimize the complexity of this study, which could have been quite complex, we wanted to test specific elements, so we narrowed the scope down and we applied a lot of assumptions. So I'm going to quickly sort of run through some of the assumptions so that they're super clear, because everything's sort of based on the assumptions in energy modeling. So for air tightness, we applied 3 levels of envelope tightness from code minimum to passive house with a step in between. For the respiration part of the study, we looked at just a single person in a bedroom with a normalized metabolic rate, 8 hours of sleep, and then some assumptions for the gas exchange occurring during respiration, percentages going in, percentages going out. When we looked at gas and particulate, we made an assumption for the CO2 levels in outdoor, and the recommended indoor CO2 levels, we landed on about 1,000 parts per million. And this was based on a series of studies, health studies for the impacts of CO2 levels, and all of them sort of suggested around 1,000 parts per million is when negative health impacts start to show up. For particulate matter and pollution, air pollution, we looked at PM 2.5 levels as a proxy, and the level we looked at for outdoors, our starting level, was about 16.9 micrograms per meter cubed, which just happened to be the level of PM 2.5 in New York City when we started the study. And then for infiltration, we only looked at infiltration on the exterior wall. So these are sort of 3 general layouts that show the apartment plan, bedroom and living room, both having being adjacent to the exterior wall. So we didn't consider air movement between apartments or from the corridor spaces or common areas, just to kind of simplify it. In practice, obviously, when we have exhaust-only scenarios, makeup air tends to come from various different places. It gets quite complex. It's not recommended to have makeup air from the corridor for health and safety, so we just limited infiltration to the exterior wall. All right, and then we built a 3D model using eQuest simulation software. We built a model for an apartment of 550 square feet, 110 square foot bedroom, about a total of 18.5 feet of exterior wall length. We only looked at mid-level apartments, so we didn't look at infiltration from the roof or the floor. And we looked at air changes per hour for infiltration, which allowed us to build the apartment and rotate it around 360 degrees and then apply a weather file to it. And that weather file had actual wind speed and direction. And so we were able to take an average wind speed and direction and find an hourly average. We applied some loads to the space, lighting, plugs, and occupants. And ventilation, we looked at a scenario with no ventilation first as sort of a baseline to see the air quality and energy consumption. Then we applied ASHRAE 62.2 2016 values for whole house ventilation, exhaust requirements, kitchen and bathroom, landing on a total of 60 CFM, exhaust requirement being the dominant flow. And then we applied some systems assumptions. So all of the apartments had package terminal heat pumps, with ASHRAE 90.1 2016 minimum efficiency levels in fan power. For the exhaust-only scenario, we looked at a rooftop exhaust using fan power from similar projects of similar size and design. Trickle vents were the makeup air source for the exhaust-only scenario in both the bedroom and the living room. And for the ERV scenario, we used the basis of design of Renew Air HE2 model with effectiveness ranges from 50 to 85%. And we also looked at 1 per floor ERVs versus a rooftop ERV unit. We also looked at filtration, and 2 filtration levels we wanted to study, the MERV 8, which is essentially the code minimum, and then an upgrade to MERV 13, which comes with an increase in static pressure. So we wanted to look at how the fan power varied for the 1 per floor unit and the rooftop units. We did also want to look at reduced ventilation flows to meet the passive house balanced ventilation levels to see how this could affect energy consumption as well. And the metrics we were looking to study, the CFM of outside air moving in and out of the bedroom, PM parts per million of CO2 from starting, which is equal to outdoor levels, to after 8 hours of sleep, PM 2.5 levels from starting to after 8 hours of sleep, and then the heating and cooling fan energy, and any additional benefits and downfalls of each scenario we wanted to include in the analysis. All right, so digging into the results. So the first graph here is looking at CO2 parts per million in the bedroom alone from starting as they started to sleep until after 8 hours of sleep. This is a single person respiring in a bedroom for 8 hours, no ventilation on these top 2 lines here, and then when we applied ventilation with exhaust only or ERV units. So we can see without ventilation here, these top 3 lines, the CO2 parts per million exceeded our 1,000 parts per million threshold that we set in less than an hour, about 3/4 of an hour. After 8 hours, the range of CO2 parts per million was between 4,000 and 6,000, which at these levels we can expect respiratory, visual, skin-related symptoms, headaches, poor concentration, inflammation. And without ventilation, you can see the trend line here. This is only going to increase. Only with ventilation are we able to curb that and bring it down to an acceptable level down here with the ERVs and exhaust-only scenario. So zooming into those, we can see that with ventilation, the CO2 levels level out. The exhaust only, at least down here, the exhaust only scenarios, we have 3 scenarios with the varying infiltration rates, and they're about the same, so it looks like one line here. And they leveled out at about 780 parts per million in around an hour. And then with ERV units, they leveled out right at around our threshold of 1,000 parts per million in about 2 hours. And the difference between these levels here is based on our design. So the exhaust only scenario, you can see the layout here to the right. We had our 40 CFM of kitchen exhaust, 20 of bathroom required by code. That's a total of 60 CFM of exhaust, applying a negative pressure evenly on the exterior wall here, resulting in 30 CFMs coming through the living room and 30 coming through the bedroom trickle vents. So we have 30 CFM coming through the bedroom here for makeup air. With the ERV scenario, by design, we decided to provide only 20 CFM of supply air to the bedroom. That way we could meet our threshold for CO2, but we could have a slightly quieter air delivery. And because we're delivering the air more efficiently right to the bed area, we can then put more air into the living room where people spend more time. If we wanted to increase this rate to 30 CFM to be in line with the exhaust only scenario, these graphs would shift down and the curve would end up trending pretty evenly there. So this is kind of the case for ventilation. This is why we have ventilation, right? You can see pretty clearly in a confined space with no ventilation, we have problems. And this really is a reminder to be very careful with ventilation and to take it seriously. So then next we looked at PM 2.5 levels, and So the red dotted line here, this is the World Health Organization recommended PM 2.5 levels for health and safety. The blue dotted line up top here, that is what the PM 2.5 levels happen to be in New York City when we did the analysis. So after 8 hours of sleep, we see that the infiltration and exhaust only scenarios, the PM 2.5 levels don't change. There's no filtration, so the inside equals the outside. Only with ERV, where we have filters, are we able to reduce the PM 2.5 levels. And just noting here, this is a reduction based on that lower CFM of 20 CFM in the bedroom that we use with the ERVs. So using a MERV 8 filter, we were able to reduce down to about 14 PM 2.5 in about 2 hours. And then with the MERV 13 filter, they were able to drop all the way down to between 3 and 4 micrograms per meter cubed in about 3 hours. That's a 3 times reduction and gets us below the World Health Organization pretty quickly, the World Health Organization threshold there. So again, this is a great example of the importance of controlling and filtering indoor air quality. This is also just the PM 2.5's level at the time of analysis. Shortly after this analysis, the PM 2.5 levels in New York City rose to about 15 times higher than the World Health Organization levels due to the wildfires in Canada. And, you know, often in those situations, indoors is the only respite people can find to, you know, take a break from that, from the air quality. And, you know, if we don't have control over the inside, we're not filtering it, you know, even a little bit of filtration is going to give us a little bit of a break there in from the health benefits, the negative health benefits. It's also important to remember that PM 2.5 we just used as a proxy for particulate matter in general. There are a lot of other pollutants in the air that end up indoors. So these two graphs show us the importance of controlling the outside air, tempering it, delivering to where we need it at a lower rate, adding filtration. But what is the energy penalty of this? And that's what we wanted to look at next. And how does this balance with the energy we can save by recovering heat that's ejected out of the building with the exhaust system? So here we start to look at energy consumption. So this graph here, when we looked at energy consumption, we looked at the whole apartment, not just the bedroom anymore. So we wanted to evenly compare the different systems. We did also include the passive house reduced ventilation flow rates, which is off to the right here, the PH vent. That's where we reduced the kitchen exhaust from 40 CFM to 25 CFM. The base load in green here, that represents lights, equipment, occupancy. The rest of these are heating, cooling, and fan energy. So we can see a clear relationship between infiltration here. We have the 3 different types of infiltration for each run. The blue is 0.4 CFM per square foot of exterior wall, then 0.25 and 0.1. We have our infiltration only scenario on the left, and then exhaust, and then our 4 ERV scenarios with varying effectiveness, and the one on the right is that passive house ventilation level. So we can see in each scenario, by reducing infiltration, we save energy. Better air sealing means reduced heating energy and conditioning fans. The infiltration only scenario here is just for reference. Obviously, this is not allowed by code anymore, but it is important to think about this is still the case in a lot of existing older residential buildings that rely on windows and doors for ventilation. The ventilation only or infiltration only scenario, we see higher cooling load and lower heating because we're not dumping cold outside air into the space. The rest of these show our energy penalty for ventilating. The exhaust only is the highest consumption here. We have a lot of untempered air being dumped into the space and quite a high fan power for the rooftop exhausts. The ERVs for the next lowest with a reduction. We can see a reduction as the effectiveness of the ERV increases, 50%, 70%, 85%. And then as we reduce the airflow rates, this obviously increased our savings more. But this is just looking at total energy. And as we change the effectiveness of the ERVs, the heating energy changes, the cooling changes a little bit. So we wanted to just compare the fan power explicitly. So looking at just a fan power comparison here, we can see that the ERV units have exhaust and supply fan power, and that total fan power is a little bit higher than just the exhaust, which makes sense because we have 2 fans instead of just 1 versus the exhaust only. There's also a higher static pressure to overcome with the heat exchangers. But because of the heat recovery, the conditioning air fan power is lower. So the total fan power ends up still being lower for the ERVs over exhaust only. There's also no significant increase in fan power with increasing effectiveness of ERVs. So there's no increase in operational costs with different ERV effectiveness, telling us the main hindrance to high performance ERVs is just the first cost. We also see the effect of reducing the ventilation flows. That is obviously going to be our biggest energy saver. One interesting thing I want to point out here, if I go back, oops, there we go. If I go back, you can see that the lowest consumption that we see here occurs with the 85% ERVs, low passive house ventilation flow rates, and good infiltration. And we end up with an energy consumption here that is, wait, let me see if I can get a pen here. There we go. That is, oops, there we are. There we go. We end up with an energy consumption here that is in line with the infiltration only scenario. So what this tells us here, everything above this line is the penalty of ventilation. That's what we have to bring the air in with fans and then condition that untempered air to the temperature that we want. This is the penalty. And once we get down to passive house level flow rates, high efficiency energy recovery, good airtight building, we can then essentially offset that penalty almost entirely and bring us back down to a case when we didn't bring in any ventilation. That's kind of cool to see. All right, then we wanted to compare what happens if we increase the filtration. If we want to have better indoor air quality, we increase the filtration to MERV 13s. Here's the energy consumption. We can see very small increase in energy consumption here between MERV 8s and MERV 13s. Only the fan power really is impacted. So if we look at the fan power, this is the fan power alone. You can see between MERV 8s and MERV 13s, there is an increase in fan power, which makes sense. We have 4 filters on each airstream in an ERV. The fans have to work a lot harder to overcome the increase in static pressure. So the 85% effective ERV here with the lowest kind of code level infiltration, that ends up with a fan power consumption that's a little bit more than the exhaust only strategy, but every other scenario still has lower fan power and much lower total energy consumption. So that was good to see. But this analysis only looked at floor level ERVs. Floor level ERVs are the preferred approach because we have lower static pressure, but often we see ERVs in rooftop scenario, and that has a lot more ductwork to a lot higher static pressure to overcome. So we also wanted to compare rooftop ERVs with rooftop exhaust only scenario. And here's the energy consumption there. We can see there's a little bit of an increase in total consumption. But again, still lower for all of the ERV scenarios in the exhaust only scenario because of all that heat recovery. And again, once we get down to passive house level ventilation rates and high energy recovery, we're offsetting that ventilation, additional ventilation load almost entirely. Looking at just the fan power of rooftop ERVs, now we see that with that increased static pressure in a rooftop ERV unit, there is definitely an increase in fan energy. And now the fan energy for the ERV units is greater than the exhaust only scenario. However, the total consumption is still much lower in the building. And then as we increase effectiveness, we see increased savings to be expected, and the passive house level flow rates again widens the gap in savings and reduces the ERV fan power to lower than the exhaust only scenario. Finally, looking at our rooftop ERV MERV 8 versus MERV 13, still much lower than the exhaust only scenario. And our fan power with the MERV13 filters does definitely increase now. We're looking at about 0.1 kilowatt hours per square foot of increase from MERV8s to MERV13s in just the fan power. But overall, total energy savings still much lower. So based on this small increase in energy savings or energy consumption from MERV8 to MERV13, we can safely say that moving to MERV13 filters with any ERV effectiveness would still result in lower energy consumption for rooftop ERVs over exhaust-only scenario. So quickly looking at additional benefits and concerns here. Comfort. So tempered air being delivered right to our delivery point versus untempered air being dumped through a hole in the facade or through cracks in the facade, definitely concerning. Ventilation health, we're able to deliver fresh air to where the people are versus having no control over where that goes. Respiration health, filtration allows us to remove dust, mold, pollen, smoke, etc. And then building health, uncontrolled ventilation or uncontrolled infiltration can mean potentially humidity building up in walls, which can cause mold. And that mold can potentially compromise the insulation, the structural members. It's hard to diagnose, extremely expensive to open up the walls and try to find it. Odor can be an issue with a negative pressure created by an exhaust-only scenario. We talked about that. Makeup air can come from various sources and sometimes bring odors from adjacent spaces. And potentially can be a fire hazard, allowing fire and smoke to spread more quickly. All right, so quick summary. The exhaust-only scenario resulted in higher annual energy consumption in almost all cases, regardless of the ERV effectiveness, filtration levels, or if the ERV unit was one per floor or a rooftop unit. As effectiveness increased in the ERV, savings increased, and these were further widened by reducing the airflow levels. There is an additional fan power with ERV units, but this was small in comparison to the total conditioning energy saved. Exhaust-only scenario ejects all that conditioned energy to the outdoors. The one per floor ERV unit showed the best performance. We'd still want to analyze per unit exhaust-only scenario for a comparison there, something to add to the study. Filtration provided our only method of improving air quality, 20% reduction for MERV8s, 85% for MERV13s. There was a static pressure increase to overcome, but this was overcome by the total ERV savings. And we saw further benefits to strongly recommend ERVs over exhaust-only strategy in multifamily buildings. Would like to add a simple payback to this analysis to consider the increased first cost and the payback period. And that's it. I want to thank all the people that helped me with this study. And if you have questions, let's dig into them. Thank you.
Thank you so much, Seth. There are many questions, don't worry. And I think that that's just a testament to how interesting and needed this is. And we need this information to be able to talk about this, as well as convince people that this is the right way to go. And this is really helpful information to start with. So yes, lots of questions. I don't want to delay those. It's also just crazy to see, you know, how much of a difference filtration and different filtration levels impact air quality. So yeah, really cool visuals, and the people want more. So first we're going to go to a message from our sponsors, and then we'll get into all these questions. I think.
I
Zach,
think
are you there?
Kim and I are like, are you doing it? Are you doing it? Are you doing it? So I am very happy to do it. So a big thank you to our stakeholder partner, NYSERDA, for support of Passive House Accelerator. Everything we do at the Accelerator, including Passive House Accelerator Live, comes thanks in part to the support of these fine organizations. So NYSERDA is our stakeholder partner. Thank you to our founding sponsors, 475 High Performance Building Supply, Ingui Architects, Glavel, Minutair, Partel, Rockwool North America, Stocorp, and Zola Windows. Thank you to our champion sponsors, Bewizo, Gradient, Icon Windows and Doors, Intelligent Membranes, PH Air Seal, and Source 2050. And thanks as well to our patron sponsors, Brennan, Euroline Windows, Holstrom System, Inotech Windows and Doors, Lamelux, Longboard, RDH Building Science, and Sanderson Sustainable Design. Thank you, sponsors.
Thank you, Zach. And before we get into the live Q&A, we're going to queue up our personal favorite question to ask every one of our next-gen speakers. And that is, what do you, Seth, think the future of passive house and high-performance building design and construction is?
Yeah, so I'm a big fan of passive systems and obviously the passive house envelope concept, but from a mechanical designer perspective, I'm super excited about passive ventilation systems. I'm really hoping we start to see some more of those be integrated a little bit more frequently in modern buildings, even commercial buildings. So that's something I'm looking out for, and the technology to sort of make that possible in a commercial space. But in general, I think I'm just more excited to see passive house being adopted across the board just as an industry standard. People being more aware about it and just realizing that we need to do this for all buildings, not just for our special buildings.
Hear, hear. Passive is the future. It's the present and it's the future with a PH. Awesome. Well, there's been some lively chat and questions in Q&A, and I do just want to make a quick plug that this study will be available at some point, thanks to the funding of NYSERDA, as this was part of NYSERDA's Buildings of Excellence early design support study work. So that's exciting, and hopefully will be out on the street available soon, but the recording will also be available as well. Mark Rosenbaum, you had some comments, questions. Some of them got answered, but if you'd like to unmute yourself and add to the conversation.
I actually don't have anything else to say and add. I thought it was a great presentation and lots of great questions in the chat. And as an old person, like the past generation, I'm very happy to see what young people are doing today. We need to pass the baton because us old guys are getting really tired. Thanks so much, Seth, and the rest of you.
Thanks, Mark. And Seth, you mentioned it. I mean, we're learning from the past, right? There were passive ventilation systems in antiquity that worked very well at what they were designed to do. And if we can start to implement more from what we learned from the past in the future, we'll be headed in a better way.
Yeah, Seth, you should call me at some point, and I have a lot of experience with some measurement and of lower energy ventilation systems. And let's just say, as a summary, I'm really glad we have fan-powered ERVs.
Absolutely, thank you.
Maybe we'll have Mark on another program to give the history of that. Those studies. I think that would be really interesting. I think I'm listed up next here, and I was wondering, Seth, if any of these scenarios in the studies included trickle vents, or if it was just based on air tightness as measured without trickle vents assumed. There was a comment in the chat that mentioned, and I think it was Mark, saying that trickle vents don't necessarily actually funnel outdoor air to the space, which I could imagine being quite reasonable. But yeah, curious whether they were included.
Yeah, so the exhaust only scenario considered trickle vents. There's a trickle vent in the living room, trickle vent in the bedroom. We are all aware of the lack of reliability, let's say, on trickle vents. And that certainly was a question that came up often around this study. Well, what if the trickle vents don't work? Well, what if the trickle vents are blocked off? What happens? And it's a complicated answer, right? it's hard to know exactly where air is going to come from in a system like this. There's a lot of possibilities. There's so many variables as far as the interior envelope, the exterior envelope, the duct system feeding all of the various stacks of apartments above, and the equation starts to get more and more complicated. So that's why we sort of simplified it in this study, and we just looked at one makeup air source through the exterior facade and the trickle vents. We do have a discussion section in the paper once it comes out, where we talk about what happens in these other various scenarios from sort of a high level. But yeah, it gets quite complex, and it gets quite difficult to try to guess at the air quality that's starting to come from the corridor, that's maybe feeding from other apartments, and on it goes. But it's a valuable question, and let's just say it's important to acknowledge that trickle vents don't always work, and they certainly are not the only source of makeup air for our exhaust only scenario.
Thank you. Yeah, that's helpful, and there were definitely some follow-up questions regarding whether, how much air infiltration is assumed between apartments, and good research requires more good research later on.
And I can't say, like, in the exhaust only scenario, if two adjacent apartments have equal exhaust, theoretically there should be no party movement or movement between party walls. But again, we're assuming excellent air tightness in the entire apartment envelope, and that's not realistic.
Mark, it looks like you had something to add with your hand up there, and then we'll go to Tom Phillips next.
Just a quick way to think about that. So the trickle vents, I don't know all trickle vents, but the trickle vents that I used many years ago had about 4 square inches of effective leakage area. So if you calculate the effective leakage area of the exterior and all the party assemblies, you can get a sense of where you think that air is going to come from. And all my calculations in multifamily buildings make it no way. And I'm sure some of you can tell me about multifamily buildings that are built with party assemblies as tight as a passive house exterior, but I have not experienced that myself yet. And so that's why I'm skeptical about pressure actuated inlets like that. And then Lois can tell you from the work that Stephen Winters did, 20 years ago, Mark Zulawaga, about what happens with tall buildings and the stack effect and how it overrides pressures that we impose by mechanicals on the building. So thank you for letting me add that little bit.
Thank you for adding it. Tom Phillips, if you want to come on, you had more of a question related to the outdoor air and assumptions around PM levels by hour. And if not, I already halfway asked the question, so I can finish it for you if you're not able to come on. So Tom was asking, read the timing of the ventilation cooling. How much do outdoor PM levels typically vary by hour and day?
That's a good question. I'm not sure. I pulled the PM 2.5 levels from sort of a live reading where you can see hourly level ratings. I think that's a good place to sort of answer that question, is to dig in and take a look. I just took a snapshot. I just happened to say, okay, what is it right now? I took a snapshot and it happened to be, relatively high. And then, as I mentioned, got considerably higher about a week later.
That's cool to hear that that data was used as part of the model. All right. Next up, we have George Ostro. Do you want to come on and ask your question?
Yeah, hey, Seth.
Hi, George.
I believe you said this was for one person in a bedroom. Is that right?
Correct. Yep.
What happens if you put 2 people in that bedroom?
Good question. I'm sure we reach dangerous levels of CO2 pretty quickly. Although I should be careful saying dangerous levels of CO2. The research shows that CO2 serves as a proxy to help us understand the oxygen levels, a better way of framing it.
But then would the the ventilation flow rates need to increase, the energy use increase, would just sort of scale up, or should we put 6 people in a bedroom?
Yeah, I think I mean, it definitely would scale up, and it would be good to sort of to look at that. And that's why we have ventilation rates that are based on number of people, right?
And Lois, you were also very active, and I don't know if you had any open questions or some other comments you want to throw in from previous research.
It looks like Lois jumped off the call.
Okay, thanks, Kim. Carrying on legacies of research, for sure, done by other firms. Next up, we have, I think we got through, well, George had another question and Tom had another question. George, if you want to ask your other.
Yeah, I mean, you kind of answered it at the end, was the cost question, which is that the simple payback needs to be analyzed. But it seems like the main objection from a building owner is how much the ERVs cost up front. But you pointed out there's a significant operational savings over the lifetime. And I'm wondering if, the curves cross in 5 years, 10 years, something that would make this, a no-brainer economically.
Yeah. Yeah, that is really the big piece that needs to get added to this, is that simple payback analysis. I think that really is, at the end of the day, one of the biggest motivators typically when we're presenting this to the team. I think typically we've seen a relatively good payback on ERVs, but it really depends on the ownership, the type of ownership structure. Is this something that's going to be owned for a long time or not? And that's always the trick as an energy consultant, is trying to make that financial case. And a lot of these things like, air quality, health of occupants, it's hard to put a value on that and see where the simple payback is, right? But just from an operational standpoint and capital versus payback, ERV usually makes sense for most all projects.
Yeah, I'm wondering if you've also thought about looking at like worst case scenarios with the air quality, like a wildfire event and what that looks like with all of these options, because I imagine that would be very effective at convincing people on top of the energy aspect or day-to-day air quality aspect of it.
Absolutely. Yeah. And I think that's something that more and more people are, becoming more personally aware of, right? As we experience these personally more and more every year. And, there's like, what do? You hide inside. That's the only thing you can do, and hope that you have some kind of filtration. And I have colleagues at Bright Power that will tell you the indoor air quality, where sometimes during that wildfire event was absolutely terrible, So you really are relying on these indoor systems, the ability to filter in those situations. And, there's going to be an increased maintenance cost with having to change the filters more often, but it's a hell of a lot better than just breathing all of that in.
Absolutely. I think we have Tom Phillips. Did you have another question that you wanted to ask here? Or maybe you weren't able to unmute before, I can't remember.
I had asked his first question, and Zoe, I think you should ask his second, because it's very topical to filtration and what you were just talking about.
All right, we've got non-energy benefits such as health and cognition. What is evaluation of better ventilation and filtration?
Excellent question. There's a lot of research backing the benefits of increased ventilation, better air quality. There's extensive, really easy to find now, which is nice. We've seen those increase over the last 10 years significantly. Now we have a lot of research to back it up. We can show increased performance in office workers, in school kids, better test scores. We show reduced healing times in hospitals. So all kinds of incredible research now to show the importance of better ventilation, increased ventilation. So yeah, there's plenty out there. Just dig in and you can find it.
Next up, we have Peter Rep. Did you want to unmute and ask your question? Or maybe it was a comment.
It was a Pandora's box of ERV versus HRV conversation, depending on climate, which I don't know if we want to open now or save to the end. That might be a more long-winded.
Pocket that one.
Yeah.
All right, then we have Aditi. Are you there? All right, we'll ask your question for you.
Nope.
Whoop. Nope. Okay. Have you investigated retrofitting ERVs into single-family residences as well? If so, what were your findings with respect to improvement in indoor air quality?
I have not. Don't work a lot in single family, but I think that is a fantastic idea. I mean, retrofits obviously is a huge market that we need to focus on for energy consumption and health. And that's sort of the next big animal that designers and consultants are starting to tackle. New construction is pretty safely moved towards energy efficiency, at least to some degree. And now we need to tackle the massive building stock of existing buildings and what we can do to improve them. Single family is often sort of overlooked if it's not a new construction. So I think that is a really important focus.
Shoot, I was hoping Mark had an answer to that, but he's confirmed he has not done a before and after measurement. That sounds like a personal unfunded project for anyone that is doing a retrofit anytime soon of their home. Justin Taylor, I see you. You hopped back on.
Oh, Mark has a hand up, maybe to respond to that really quickly before we move on.
So I just wanted to say about retrofits, because it's a great question. The thing about retrofits, when you're starting a retrofit project, to me, I'm always asking the occupants, what are all the deficiencies of the building? And so air quality comes up over and over and over again. And so you're dealing with things like mold or combustion reentrainment, all kinds of things. And I think the assumption is if you're really dealing with the building on a holistic basis, you are absolutely going to increase air quality benefits, and you don't have to measure it. It's going to be so much better than what you started out with. So as long as you don't view it as only an energy project, I think you're going to make people's lives way better. And the benefits to the people inside are so much more what the living environment is like afterwards. Their energy bill is so far down on the things that really matter to people. Thank you, Zoe.
Right on. Thank you, Mark. And Justin, you are up.
Hi, can you all hear me? All right, cool. Yeah, so my question was if there have been any other studies that have looked at noise levels when comparing, either the floor by floor ERV layout or unit layout versus a centralized layout. And I only bring this up because I've heard of a few projects where the noise issue has become a little bit of a problem, specifically for central ERVs, where like you see some people actually blocking off the supply air vents because the air flow is higher than like when you have a unit ERV.
Yeah, it's a good question. I don't have a good, clear answer for it. I will tell you that the Renew Air models and also Ventacity, there are a couple sort of smaller one per floor size ERV units that are appropriate for this type of design. I've seen those models up close and I've seen them running. I've heard them running and they're remarkably quiet. I think, once you get to the larger units, rooftop units, obviously you've got, they're going to be louder, but they're on the roof. But then you have what you're talking about is a duct airflow.
Yeah.
If
Mhm.
with correct design at these lower ventilation flow rates, there really shouldn't be a lot of noise, unless the design is not done well as far as register selection and such. But maybe there is another issue I'm not thinking of, and if anybody else has any insight on that.
I can maybe add a few thoughts and anecdotes here, especially on the central side, because we have been in post-completed occupied buildings where we've gotten complaints or there's just confusion around why they're hearing, they think their AC is off and they're hearing the airflow continue to come through and they're sensing that as discomfort. So some of that is education. Some of it is truly what Seth is talking about, is the duct design appropriate for the static pressure drop? Do the central ERVs need silencers, which some of the larger units now do have, and depending on the static pressure drop, they'll require them. PHI has a requirement for that. Interestingly, we got an anecdote from a certifier that we've been working with, that a project that had completed already did not install silencers on their ERVs and were not meeting that PHI requirement, went back and did a survey of occupants and asked them, do you find this to be a uncomfortable amount of noise? And that was in New York City. So uncomfortable amount of noise in an anecdotal survey of occupants is very different depending on what you're used to for noise. And that gets off into a whole other topic. But so there are both, like measured and engineered solutions for noise. And then there's like, what is a comfortable level of noise? And can you educate the occupant around why they're hearing airflow?
It's so much about education and just about what people are used to. Like if they don't know what their systems are for, what they're like, that they even have a ventilation system, then they don't know to expect, a little bit of noise. But maybe if they knew they had this really effective ventilation system, they would be happy to hear that it's kind of going a little bit in the background. So I do think that there's so much to be said about occupant education, regardless of how much they actually need to be doing something, to upkeep, filter changing or whatever it may be. So fantastic point.
Yeah, thank you for that question, Justin. And definitely if you're speccing a central system and you're worried about the top floor occupants, check in with the manufacturer of that central system and make sure that the design of the ducts is, not triggering the need for silencers. And then I think we had one more person in the queue, Ty. I hope I'm pronouncing that correctly. If you want to come on and unmute yourself.
Hi, yeah, no, you're saying it right. My son's with me today, so you're gonna hear a tiny voice in the background. Thank you for the presentation, Seth. And you made a great argument for a lot of existing building owners to consider putting ERVs in their building, and it goes beyond just energy benefits. It's the whole air quality, and I didn't realize how much a difference it made, especially with that drop off that you were showing on your charts. My question was relatively, it might be where I'm from, which is very specific, and I know it kind of drifts away from your presentation, but I haven't often seen floor ERVs. And is there an argument for floor ERVs versus in-suite ERVs? And then with the in-suite ERVs, there's like even two different styles. There's like integrated and the one that sits above your washroom. But if you were to choose a floor ERV versus integrated, what would that be? Do you see a passive house argument for floor ERVs because you have one penetration versus several?
When you say floor ERVs, can you elaborate on what you mean there?
Well, I assumed it's one ERV serving all the suites on the floor.
One per floor unit, yeah, versus sort of
Yeah.
a one central rooftop unit.
Oh,
Yeah.
no. Well, the other one was per each suite.
Oh, for each suite.
Unitized. Yeah.
I see. I understand. Yeah, I understand what you're saying. Yeah. I mean, absolutely. I think anytime we can minimize exterior envelope penetrations, we should. Absolutely. And to that point, rooftop ERVs got the best minimal penetrations there, right? We have one penetration in the roof, but then it comes with a balance. It's finding that sweet spot between performance and the compromise of our envelope penetrations. I think as far as effectiveness in the ERV units and fan power, effectiveness is going to be, from what I can tell, pretty even across unit sizes. Really what it gets down to is fan power, and fan power is the big compromise there with the ERV units. We're already adding more static pressure to overcome the heat exchanger and filters. That's our penalty, and that's what we're trying to make up with our heat recovery. So as we increase the larger unit, more ducting, we add more static pressure, increase in fan power, and those savings get less and less and less. So we have to sort of find that sweet spot. And it seems like the industry sort of settles on the 1 per floor as that nice sweet spot for effectiveness, minimal penetrations, and low enough fan power that we can really see the benefit of the savings.
And then, in practicality, there's this balance to be struck between, being able to balance as well as service and change filters and things like that. So I would imagine that would kind of add to that argument. Mark's giving thumbs up.
Definitely, yeah, that is an important point to acknowledge, right? I mean, anytime we have filters, they need to be maintained, absolutely, especially on our ventilation airstream, right? Crucial. So yeah, that is a great point.
Especially when we're talking about multifamily rental units, affordable housing, spaces that are harder to get into regularly, and paired with that occupant education piece, right? Do they know when to call and ask for a filter change if something's gone awry? Mark, you had your hand up.
I just want to add to that. I mean, to me, I'm working on multifamily, and I don't work on really big multifamily, but sort of maybe 6-unit buildings. As much as possible, I'm trying to keep maintenance people out of 10 units. And but the other thing about having central maintenance and people really paying attention, you begin to learn the building and where it is. And like I found out just with my own, I think I live in a clean place. I live on Martha's Vineyard in the sticks. My supply air filter plugs way faster than my exhaust air filter. And what happens in a really tight house is that the house goes negative. And I can track whether I need to change my filters by the radon measurement, right? Because the house is going negative and the radon is going up. So, so I think the fewer ports you have to outdoors, the fewer places you have filters, the more accessible you can get to those filters. But you might find in another kind of building that it's the opposite, and the exhaust filters are plugging up faster, and there may be smokers, and there may be pets. There are all these different reasons. And so to some extent, to having a building maintenance staff that really learns that building as opposed to the statistical building that we all have as our mental model, that's really useful over time.
Yeah, and I've definitely consulted on a few buildings where the prospective owners wanted to be able to get into the units and use filter changing as an excuse to do so. So it certainly matters, who owns the building and who the occupants are and what their tendencies are. So absolutely agree. We had a question come up recently. Where did it go? Justin said, I've always preferred floor by floor ERVs, but they are not allowed in New York City, correct? I think the team in New York City can probably reply to this.
Yeah, there are. Oh, go ahead, Seth.
No, I was going to say this one's for you.
They're allowed. There's definitely other reasons and limitations in New York City why it might be challenging to implement them. So I can't say that, yes, they're allowed and you can do them on any project. Sometimes there are like lot line limitations or other things where locating the terminals is difficult. And then so you have to figure that out. But you can do that with setbacks, and you can do maybe not floor by floor, but like, chunks of floors. And there's different ways around that for sure. But they're not outlawed.
But wasn't the issue also that you can mix in the bathroom and kitchen exhausts like between units? Right? Wasn't
Yeah, that's been kind of a
Debunked.
yeah.
oh, okay, that's great to hear.
And was a central ERV issue as well, but definitely overcome with a little explanation when I last left it, but that was what, 4 years ago. So maybe it's even more common now to be able to get around that.
Yeah.
I would certainly caution people when using kitchen exhaust to an ERV, though. Definitely be careful with that. We don't want to foul the heat exchanger. The heat exchanger effectiveness will drop significantly and potentially require entire replacement once you have it fouled up with kitchen grease. So that needs some thinking before you jump to that.
Right. There are extra requirements around locating the grills a certain distance away from the cooking grease and adding filters at those grills to mitigate that. And Laura, I guess debunking wasn't the right word about that code requirement of consolidating exhaust streams. It was more that there were waivers filed enough times through code that they have, kind of made it more acceptable and allowed, and it's not a hurdle that you have to jump through every time with the DOB now.
Well, we are technically over time already, which was expected given how many questions and how much interest there was in this presentation. So thank you so much again, Seth. Really appreciate you and the whole team for doing this work and sharing it with us. And we look forward to the publication and being able to reference it and look even deeper into these things and any follow-up study that comes along after. So yeah, thank you very much. Next month, we have Karno Wijaja from Brunner Architects in Boston joining us. And let's see, are we staying on for any more? Were there any more questions that came up in the chat, or are we ending it at the hour?
Feel free to reach out to me personally if you have other questions. I'm happy to answer as well.
Thank you so much. Thanks,
Yeah.
everyone.
Thank you again, Seth, and thanks everyone for engaging. Take care.